Okay, so today we will discuss the few tests uh, which will decide about the convergence or divergence of the improper integral. We have already discussed these two examples. The first example which we have discussed, a to the power a integral a to infinity x to the power minus n dx. This is where a is greater than 0. This is an improper integral of the kind 1, and we say this integral converges if n is strictly greater than 1 and diverges if n is less than equal to 1. So this we have seen as a example, and it will be used for future work. Another example which we have seen, if the function is not defined at the endpoints, that is function becomes unbounded at the either a or b, then in that case we can also have a convergent test, and for which this example will be helpful. So we have seen this example 0 to a x to the power minus n dx, where the function becomes undefined, is not defined at 0. Hence this is a improper integral of the kind 2, and we have seen this integral converges if n is less than 1 and diverges if n is greater than or equal to 1. So these two examples we have seen, and then we wanted to generalize this theorem, particularly this result, algebra this result for an a improper integral to test whether it is convergent or not. So these examples will be used. So first we will go the convergent test for indefinite integral, for infinite integrals. So the first test we say is a comparison test. The comparison test say we know if fx is greater than 0 when x is greater than a, then this integral a to x fx dx is monotonic increasing. It means when x increases, the corresponding value of this integral will increase. Therefore, if we say that this integral converges, this gives an idea. Therefore, we say the improper integral a to infinity fx dx converges if the integral a to x fx dx remains bounded by k, that is, the value is always be less than k for all values of x, where k is a fixed number. This is a fixed real number, some positive number. So if this is true, then we say this integral converges, because this is a monotonic increasing function, and for each x this is bounded by k, is less than or equal dominated by k, k is a fixed. So the value of this integral will be a finite quantity, so it is convergent, and this suggests the test which is known as the comparison test. So we have this test which is known as the comparison test. What this says is, if fx and gx are positive and integrable, and fx is less than or equal to gx throughout the interval when x is greater than or equal greater than a. It means from a onward, whatever the point x is, this condition is satisfied for all x. This is true for all x, when this is true for, in fact, all x is strictly greater than a. Okay, then the behavior of this integral, then we say integral a to infinity fx dx. This integral is convergent when integral a to infinity gx dx is convergent. It means when the function f and g are two functions which are positive and integrable, and if the right hand side integral of gx a to infinity converges, then left hand side integral f a to infinity fx dx can converge. It means if you want to test the nature of the convergence of this integral, and we are able to construct a function g for which this condition is satisfied throughout the interval x greater than a, then the convergence of this integral will imply the convergence of this integral. Okay. Similarly, if suppose if fx is greater than equal to gx for all x greater than a, and if integral a to infinity gx dx diverges is divergent, then the integral a to infinity fx dx is divergent, is also divergent. So this is known as the comparison test. It means with the help of the function f, if we are able to get g such that either this inequality holds for all x or this inequality holds for all x, then the behavior of the integral a to infinity fx dx can be judged, and it will depend on the inequality. If this inequality holds, then if this integral is convergent, then this integral will converge. Similarly, if this inequality holds and this integral diverges, then this integral will also diverge for it. Okay, so that's what we get it from here. Another test which we have all, let's take an example here, that's better, that if we take, say for example, yes, suppose I take example, p is greater than, p is less than equal to 1. Suppose I take for p is less than or equal to 1, test the convergence of the integral 1 to infinity log x ln x divided by x to the power p dx. Convergence, that test the convergence for this integral. Okay, p is less than equal to 1. Now we know for x, we know for x greater than equal to e, log of x divided by x to the power p will be greater than equal to 1 by x to the power p. Okay, 1 by x to the power p. But integral 1 to infinity, integral 1 to all e to infinity, e I will say, e to infinity 1 upon x to the power p dx, p is greater than, less than equal to 1. This is what? This is nothing but x to the power p minus p plus 1 over minus p plus 1 e to the power e and infinity. So it will go to, when you take p 1 minus p, it is negative. So we get from here is this will be equal to 1 minus p, and then this is 1 x to the power 1 minus p, p is negative, so it is basically e to v, and then take the limit v tends to infinity. is it not? So it will go to infinity as v tends to infinity, because this is positive. 1 minus p is positive, p is less than or equal to 1. So this is infinity. It means this integral will diverge, and 1 to e, it is a finite sum. So obviously 1 to e will does not contribute. If this diverges, then the total thing will die. So the right hand side, so since the integral 1 to infinity 1 by x to the power p dx diverges, therefore by comparison test integral 1 to infinity ln x or log x divided by x to the power p dx diverges. Okay, so this way we can find out the thing. Okay, then another one example is also, suppose I take this one, say another example which we take, say, okay, okay, let us take e to infinity log x to the power p integral e to infinity dx by log x or ln x to the power p, where p is less than 1, so that this integral diverges. Okay, so again we see here solution. When x is greater than equal to e, the log of x to the power p is less than equal to log x, therefore why? Because the x is greater than equal to e, log of x to the power p lying between less than 1, so it will be positive quantity. Log 1 is greater than 0, of course, so it's positive, and then when you power p is less than 1, so we get the log x to the power p is less than log x. Okay, now 1 upon this thing log x to the power p, therefore 1 by x log x to the power p is greater than equal to 1 by log x. But what is the 1 by log x? But integral e to infinity 1 by log x, and this integral diverges, is it not? So this diverges dx, it diverges. So this integral will diverge, therefore it diverges. Therefore this diverges. E to infinity to the power p dx diverges. Okay, so that's why the comparison test will be very useful, but only thing is we have to identify the relation, because if you are unable to identify such a relation, either fx is less than equal to gx or fx is greater than equal to gx throughout the interval, then only we can decide about the nature, otherwise not. The second test is mu test. What we say says, if x to the power mu fx is bounded for x greater than a, then integral a to infinity fx dx is absolutely convergent, provided mu is greater than 1. Okay, and diverges, and if okay, let's or we can say in particular in particular, if the limit of this, limit of x to the power mu fx when x tends to infinity exist when mu is exist if where mu is greater than 1, then the integral a to infinity fx dx converges absolutely 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 converges absolutely. Similarly, if limit of this x to the power mu fx when x tends to infinity exist and is not equal to and is not equal to 0, different from 0, where mu is less than or equal to 1, then the integral 1 to a to infinity fx dx diverges. Of course, proof is simple. What we do is consider this modulus integral a to x fx dx. Now, this is less than equal to a to x mod of fx dx. Now, what is given is that if x to the power mu fx is bounded, so modulus of this is less than equal to say k bounded, that is if this is less than equal to k, that is x to the power mu or mod x to the power mu fx is less than equal to k. K is some constant, for some constant k. So, we can write mod of fx is less than equal to k times integral a to x to the power minus mu dx, a to x to the power minus mu dx. Now, this integral is of the first type, integral a to infinity x to the power n type minus n type. So, if n is we have seen that this integral will converge when mu is greater than 1. So, it converges, therefore, the integral converges when mu is greater than 1, is it not? When mu is greater than 1. So, when x tends to infinity, this one, that is this integral a to infinity fx dx, this integral will converge, will converge, will converge. Because this integral converges, therefore this integral will converge. Okay, so we get the thing. Similarly, if we take the limit of this, in particular limit of this exists, and if we greater than 1, then this integral converges absolutely. Okay, so opposite of this will be the diverging one. Okay. The third test, of course, it is not very useful, but I will just simply say if fx, if integral a to infinity fx dx, this converges absolutely and gx is bounded, and integrable then integrable in the interval a to x, then for each x, then integral a to infinity fx gx dx is absolutely convergent. Why? Because the reason is consider modulus integral xi dash fx gx dx. Necessary and sufficient condition for the convergence of the integral. So, this is less than equal to k times integral xi to xi dash mod of fx dx, because this is given to be bounded. So, let it be bounded by k and this. Now, if this integral fx converges absolutely is given, so this is fine, less than equal to some quantity, okay. So, this will be converge less than epsilon. So, this shows necessary less than epsilon, and this shows that this is convergent, okay. Now, these are the general case. In particular, we say the convergence of the also case. So, in particular, we can see the cases when the convergence test for improper integral. This is particular case, okay. So, suppose it is sufficient to consider the, let fx is unbounded at x equal to a. Improper of the kind 2, of course, x in the interval ab, okay. Then this integral a to b fx dx we can write as limit epsilon tends to 0 a plus epsilon to b fx dx, and this, if this limit exists, then we say improper integral of the kind 2 exist or convergent. So, instead of going for the limit, we can go by the test, and the first test is comparison test. What this test says, if fx and gx are positive and fx is always less than equal to gx in the interval a plus epsilon to b, in this interval, then the integral a to b fx dx is convergent when integral a to b gx dx is convergent, okay. And the proof is just the previous thing, because if we take this thing a to b fx gx, then this is less than equal to gx, and gx less than equal to a plus epsilon. When epsilon tends to 0, this will converge, so therefore this will integral converge. So, it is not that. The second test is the mu test. The mu test, if x minus a to the power mu fx is bounded in the interval ab, then integral a to b fx dx is absolutely convergent if provided mu is strictly less than 1, and diverges if mu is greater than or equal to 1. So, this will be our, or equivalently we can say in terms of the limit, or equivalently in particular, if the limit exists, then if limit of this as x tends to limit of this as x tends to a plus 0 x minus a to the power mu fx exists, where mu is less than 1, then integral a to b fx dx converges. Absolutely. Okay, and in the same way, if limit of this x minus a to the power mu fx when x tends to a plus 0, fx exists and is not 0, and it's not 0, where mu is greater than or equal to 1, then the integral a to b fx dx diverges. Okay, so these tests are very important and we will make use of this test very frequently. Okay, let's see some problems. Discuss the convergence and divergence of the integral 0 to 1 x to the power n minus 1 log of x dx. Okay. Now this integral, if you see at x equal to 0, the integral, because n, if it is less than 1, then this will come in the denominator. So at x equal to 0, it is not defined, unbounded. Therefore, we can discuss it into two phases: when n is lying between less than 0, when x is n is equal to 1, and when n is greater than 1. These three cases will be there. Okay. So let us see the solution. Case 1, when n is equal to 1. Just first simple case first. What happens when n is equal to 1? This integral 0 to 1 reduces to 0 to 1 log x dx. Okay. Now this we can write it as epsilon limit epsilon tends to 0, because when it take x tends to 0, it is going to infinity, unbounded. So let epsilon tends to 0, epsilon to 1 log of x dx. Okay, integrate by part. So when you integrate by part, we are getting the value of the integrate by parts. So we get from here is limit epsilon tends to 0, first function integral of the second, say first function is log x, integral of the second is x, minus integral dc of the first is 1 by x, integral of the second this, and then epsilon to 1, and like this. Okay. So when you again integrate it, finally you are getting limit epsilon tends to 0, you will get the value to be epsilon minus epsilon log epsilon minus 1. Is it not? Because this is epsilon 1 minus, and then we are getting to be this. X gets cancelled, minus integral dc of the first integral. So here is x, which is minus 1, and then plus epsilon, and here is epsilon log epsilon. Okay. Then first one integral of the second. So you are getting this way. Is it not? X log x minus because log 1 is 0. This is 0 to 1. I am sorry. This is 0 to epsilon to be 1. Okay. So we get this. Now when epsilon tends to 0, this is 0. What about this? This we know that x to the power alpha log of x, when x tends to 0, is always be 0. Why? Where alpha is greater than 0, when alpha is greater than 0, because by using the L'Hopital's rule, if we apply the L'Hopital's rule, you will get immediately the things, because this can be written as, because this is 0 into infinity form, 0 into infinity form, so it can be written as log x divided by x to the power minus alpha and limit x tends to 0. Okay. Now when we differentiate, apply the L'Hopital's rule, so log x is 1 by x, this will give minus alpha x to the power alpha minus 1. So when you get from here is, and limit x tends to 0, so limit x tends to 0, this is minus alpha, and then x to the power alpha will go up, otherwise, so it basically 0. So this is always be 0, it means this is 0. So the limit of this comes out to be minus 1. It means the value of this integral is comes out to be finite. Therefore, this converges. So integral 0 to 1 log x dx convergent is convergent. Okay. Now case 2, when n is greater than 1, case 2, when n is greater than 1, n is say lying between 0 1 is integral is proper and 1. So when n is greater than 1, the integral 0 to 1 x n minus 1 log x dx. Now here the integrand, when n is greater than 1, this basically comes in the numerator only. This comes to in the numerator. Therefore, the integral is proper. This integral is a proper integral, because the limit of this x n minus 1 log x as x tends to 0 is 0. So this limit is 0, means it is finite, does not go to unbounded. So it is a case of proper integral. So it will be convergent. So convergent. So nothing to prove. When n is less than 1, n is less than 1, then let us denote, let fx is stands for x to the power n minus 1 into log x. Okay. Now consider x to the power mu fx. Now one thing is, when you take x to the function fx, what is the result? If you remember, the result was mu test. The mu test was, yes, if this is bounded in the interval, bounded in AB, then this is absolutely convergent provided mu is less than 1. Okay. So we can use this criteria here. So when n is less than, we find this in this x to the power mu dx for fx converges converges when mu plus n minus 1 is greater than 0, because this is equivalent to what? This is equivalent to x to the power mu plus n minus 1 into fx. Fx means log x, log x, that is, and we know the limit of this is 0 if this is greater than positive quantity. So limit of this, it will converge. Therefore, this converges when mu plus n minus 1 is greater than 0. So this implies that is the n 1 minus n is less than mu. Okay, but integral converges, but this integral 0 to 1 x to the power mu fx dx. So this is a bounded function. So this integral converges by mu test, because it is equal to the same as integral 0 to 1 x minus 0 mu fx dx. So this integral converges if mu is strictly less than 1. So from here this shows 1 minus n is strictly less than 1, this implies n is greater than 0. So this integral converges when n is greater than equal to 0, greater than 0. Already we have seen when n is lying between less than equal to 1, it is convergent, and diverges when n is less than equal to 0. So what we see here, therefore integral 0 to 1 x to the power n minus 1 log x dx convergent for 0 less than n less than equal to 1 and divergent for n less than or equal to 0. Because when mu is greater than equal to 1, it is diverging, and when mu is greater than equal to 1 means n is less than equal to 1, so divergent. Okay, so that's the result. Another example we will discuss is discuss the convergence of the following integrals. The first integral is 0 to infinity x to the power alpha minus 1 e to the power minus x dx, and a alpha is greater than 0. In fact, this is denoted by gamma alpha. Okay, so we will use the later on word gamma alpha. Okay, second integral say is 0 to 1 x to the power m minus 1 minus x to the power n minus 1 dx when m is greater than 0, n is greater than 0. So this integral we denoted by the gamma beta mn, n is not the beta function, beta mn. This converges here. So this basically this is convergent when R alpha greater than 0. This converge when m is greater than 0, n is greater than 0. So basically this is convergent. This is convergent. Okay, this we will test it. So solution is first one. Now if we look this integral, when alpha is greater than 0, so when alpha lying between 0 and 1, this x will come in the denominator, so it becomes in unbounded when x is 0 at the lower limit. Okay, and then because of the upper limit, it is a mixed, again an improper integral. So we will divide this integral 1 0 to infinity x to the power alpha minus 1 e to the power minus x dx as 0 to 1 x to the power alpha minus 1 e to the power minus x dx plus 1 to infinity x to the power alpha minus 1 e to the power minus x dx. So this is first integral, this is second integral. Okay, two parts. Now first we check the first one, first integral. Let us denote, let x to the power alpha minus 1 e to the power minus x is fx. Okay, so what we see here, we see that x to the power 1 minus alpha fx, that is equal to what? E to the power minus x, and that goes to 1 as x tends to 0. Therefore this integral is convergent. Therefore integral this fx dx will converge. Therefore this integral fx dx x to the power alpha minus 1, this integral converge alpha minus 1 e to the power minus x 0 to 1 dx converges when 1 minus alpha is less than 1, that is alpha is greater than 0. Okay. The second part of this, the function limit of this x to the power alpha minus 1 e to the power minus x when x tends to infinity, this is always be 0. Whatever the alpha may be, this power x to the power e to the power x will minus x will go in the denominator, so it will always be 0. Therefore, whatever the value of whatever be the value of alpha. Therefore, the second integral 1 to infinity x to the power alpha minus 1 e to the power minus x dx will be convergent when alpha is positive. Okay. So, this is greater than 0. Okay. Therefore, this integral converges for all. Now, second part is full. Second integral is again 0 to 1 x to the power m minus 1 1 minus x raised to the power n minus 1 dx. Here again it depends on m. Suppose m is less than 1, then at this point it is diverging. When n is less than 1, at the upper point it is again diverging. So what we do, we break up into two parts, 0 to alpha x to the power m minus 1 1 minus x n minus 1 dx and plus alpha to 1 x to the power m minus 1 1 minus x n minus 1 dx. So, we will look the convergence of both integral converges, then only this integral will converge. Okay. So, let us see the first. Okay. Where alpha is obviously lying between 0 and 1. Clear? Now, let us see the first part. Denote x to the power m minus 1 1 minus x to the power n minus 1 is suppose fx. Then what we see here is, we see that limit of this function fx when multiplied by 1 minus m fx as x tends to 0 is basically what? This is the same as limit x tends to 0 1 minus x to the power n minus 1. So, that comes out to be 1. It means it is finite. So, the first integral, therefore, the integral 0 to alpha x to the power m minus 1 1 minus x n minus 1 dx will converge provided what? Provided this 1 minus m by which you are multiplying is strictly less than 1, that is m is greater than by mu test. So, this is converged. Okay, provided this. Now, since again second part is, since limit of this 1 minus x to the power 1 minus n fx as n x tends to 1 is nothing but what? This will be the same as 1 minus x to the power uh, n minus m minus 1 as x tends to 1. So, it comes out to be 0. Why? 1 minus x tends to 1 fx. What is our fx? Fx is denoted by this one, is it not? So, when you multiply this by 1 minus x 1 minus n, so that becomes 0, and when x to the, sorry, this will go 1 minus n plus 1 minus n and then multiply by x to the power 1 minus x to the power m minus 1. So, this limit comes out to be 1. Okay. So, once this limit comes, it means it is finite quantity. Therefore, the second part will be convergent. So, second part alpha to 1 x m minus 1 1 minus x n minus 1 dx converges if this 1 minus n is strictly less than 1, that is n is greater than 0. Therefore, whole integral 0 to 1 x m minus 1 will converge for m is greater than 0, n is greater than 0. Okay, because this is true for all n and for all m, n greater than 0 and for all m, and earlier m is greater than 0 and for all n. So, common factor is m is greater than 0 and n, and this is known as the beta function. So, it will also be very useful functions. Okay. Apart from this, we will now look few more examples that is also directly for them. Okay. Let us see for p greater than 1, for p greater than 1, each integral 1 to infinity log x over x to the power p dx convergent. Okay, this is our game. Now this we will show it by first definition itself. So let us suppose we can write it this for convergence part is 1 to infinity log x over x to the power p dx can be written as limit v tends to infinity 1 to v log x over x to the power p, because x vary from 1 to infinity. So it is well defined at this point. 0 is not available. Only point when x tends to infinity, this because of the infinity it is improper. So if this limit exists, then we say the integral will be convergent. Now this you integrate by parts. So if you apply the integration by parts, taking the first function this, second function is, so we get first function is 1 upon x to the power p, first function is log x, first function integral of the second, so integral x to the power minus p plus 1 over 1 minus, so we get 1 minus p x to the power minus p plus 1, so p minus 1. First function integral of the second is log of minus p, that is 1 by p, first function integral of the second minus integral dc of the first 1 by x, and integral of the second will be 1 minus p x to the power p minus 1, and that will be equal to what? Dx. Okay, so when we again apply this integration, now it is simple integration. So when we get this integration, what we get from here is that this comes out to be the limit v tends to infinity 1 over 1 minus p log of b over v to the power p minus 1 minus 1 over 1 minus p whole square into 1 by v p minus 1, then minus 1 over 1 minus p square. Just simple integration you will see. So what we get when b tends to infinity, now this part, only thing limit of this is required because this will go to 0. So what we claim is the limit of this will be 0. So basically the value will come out to be 1 over 1 minus p whole square as limit of log b over v to the power p minus 1, v tends to infinity 0 by L'Hospital's law. That you can just verify as earlier, p is greater than 1. Okay, so this proves that. So the integral converges. Okay. Now next, if we look this again, integral second, evaluate this integral 0 to infinity e to the power minus x cosine x dx. Okay. So what we do is we are first taking this as the limit v tends to infinity integral 0 to v e to the power minus x cos x dx. Now what I say, we know that if I take I to be the integral e to the power minus x cos x dx, okay, and then taking the first and second function, first function integral of the second minus integral dc, first function integral of the second minus integral of the second is sin x, okay, minus integral dc of the first and integral of the second is sin x dx, and again first function and second function, and again repeat this thing. What we get, we will get the I again. So finally we are getting I to be do it. Okay, again, so what we get, I comes out to be half half e to the power minus x sin x minus cosine x. Okay. So now 0 to infinity of this means I 0 to v is it not? So this will be, therefore what we want is the limit. Okay, so we get from here is hence 0 to infinity e to the power minus x cos x dx, that will be equal to what? Limit v tends to infinity e half e to the power minus v cosine of v minus sine of v minus 1, because this will be, when you go for this 0 to v, okay, and then finally you will get something here, integration when you do it, this part when you do for the integration, you are getting this thing minus b and 0. Okay, so finally integration will be from here, this will be 0 to b, when you are writing integral 0 to v e to the power minus cos x dx, then you will get this result which by I am doing. Okay, this one. Okay, half of this is half e to the power minus v cosine v minus sine v. Okay, and then minus plus half, this you will get it. So when you take the limit of this v tends to 0 infinity, we get this thing. Okay, so we get from here what we get is, now the answer will be when v tends to infinity, this is bounded function bounded by 2, mod cos x is less than cos b is less than equal to 1, mod of this less than equal to 1, so this part will tends to 0 and here you are getting its half. So that will be the answer. So convergent one. Okay, so this we get it. Now one more example is, let us evaluate integral 0 to infinity e to the power minus root x dx. So here if we substitute root x equal to t square, then everything will be fine and we get 0 to infinity e to the power minus t and twice t dt, to 2t dt, and that's all. So when you integrate, you are getting the value to be answer. So it is convergent, and that's will good. Okay, thank you very much. Thanks. So this completes your course. Fine.